PDF. It's my very great pleasure to introduce Phil Chatter from I15 to tell us a bit more about the technique and the type of experiments that can be done and how this applies to catalysis. So I'll hand straight over to Phil.
Thank you, Josie. As Josie's already said, this was prompted by the award of the new Block Allocation Group time to the Cat Hub on the XPDF beamline at Diamond. The idea was to give you a bit more an introduction of what PDF is, how it might benefit your research. So hopefully get some ideas going for how you can use the bag and come up with new experiments that can benefit your research. So I'll take you through the structure of the talk. So first off, we're going to just go around a little bit of an introduction into what disorder is and local structure. Then an introduction to the PDF itself, a brief comparison to XAFs, where you already have a block allocation group on that. So a few more of you may already be using XAFs than you are PDF. Then I'll go over some aspects of the PDF data collection and the beamline itself, I15 where you have this beamline awarded. And I'll go through some examples of within the field of catalysis where the PDF has been applied in the literature. So first off, in terms of what is disorder, when people think of disorder, they tend to think of something that's just completely random, and that's not necessarily the case. More often than not, what we're talking about is systems that are disordered but have elements of order within them. And what do we mean by that? Well, here we have a couple of examples. Here we have some colored pencils on the left. Although there's no ordering in terms of color, after a quick look, you can kind of see that the pencils are lining up in a particular way. So if you were to generate a PDF of these, it would not be completely random. There's elements of order there. Same on the right-hand side, we have a disordered arrangement of kittens. But again, they're not completely disordered. They tend to line up along the body length. And as well in these, they're lined up within a roughly 2D sheet. So wherever there is disorder, there's also elements of order. How does that apply when we think of on the atomic scale? So here we have two systems that have the same number of black and yellow atoms, but the left-hand one was generated with a completely randomized arrangement. And on the right-hand side, we have ones that have some elements of clustering within them. Now, if we were to look at the Bragg diffraction pattern of these two arrangements, then we'd have basically the same information. So on this next slide here, we have the Bragg data on the left-hand side. But what you don't tend to notice when you're just looking at a Bragg data collection is actually there is information about that local ordering present. It's just at a much, much lower level. So on the right-hand side here, we've really zoomed in on the background, and we can start to see that this pooling of clustering gives rise to these extra features in your diffraction data. It's just that they're very small. If we look now on a 2D data set, as we would be if we were looking at our powder diffraction pattern, then the same, we have these very sharp Bragg peaks that come from the long range ordering of those regularly spaced dots. And then we have this extra short range ordering, which is due to those localized clustering of atoms. Now, like I said, this is well down in the background. And although we can interpret the data on this scale, what we typically do is look at the PDF, and there we can see the difference between these two arrangements. I'm going to go into a bit more detail about what PDF is in a little while. So for now, just believe me that the PDF is sensitive to this type of short range ordering. So in terms of the types of disorder that we might be interested in look at, we have disordered systems themselves. So on one end of the scale, we have these perfect crystals that have no elements of disorder. We have this whole range of other systems that have elements of disorder within them. So we might have a perfect crystal that just has a number of defects. Then we might have nanoparticles that themselves are very ordered, but on very short length scales. Then we have extremes of gases and liquids, where there is no long range order or no real medium to long range order either. Then if we go to a bit the other way, where we go to very dense fluids, then we start to see some elements of order creeping back in again. They also have these elements like quasicrystals and plastic crystals that lie halfway between crystalline and non-crystalline states. And as well, for basically any material, we always have our phase diagram that says, although there may be solid parts of the phase diagram where you're nice and ordered, at some point we'll have liquids or vapors where we have elements of disorder again. So how that might look in a system where we're looking at types of order. If we go back to our nice regular 2D arrangement of atoms again, this is a completely ordered system where we just have alternating grey and white balls. However, we could introduce stacking faults into that system, and there we'll start seeing elements of disorder appearing as these diffuse features underneath our Bragg data set. We might have things called local rules, where locally we have these atoms pairing up. Or we might have systems of these nanodomains, and there's nothing intuitively to say that any one of these things are more or less likely than in one system. And you could easily have coexistence of multiple of these effects happening within the same system. So therefore, it's quite important to characterize as best you can your materials and try to find what elements of disorder are most likely in your systems. So that's kind of the types of disorder that we might be looking at. So now we're going to go on to what is total scattering and how it relates to the pair distribution function. So in terms of total scattering, it's made up of Bragg scattering, which is our sharp peaks in our diffraction pattern, and they're due to long-range periodicity in our system. And by long range, I mean these are many, many unit cells long, repeating crystallographic arrangements of atoms. We then also have this diffuse scattering, and these give us very weak features, which lie well below the Bragg peaks, and they're related to the short and medium range order in our system. And what we mean by total scattering is that we're treating these Bragg and diffuse scattering features together in a single data set. So we're looking beyond just our average crystalline structure and trying to include the impact of these short and medium range effects. So that's total scattering in words. What does it mean in practice? So here we have a typical Bragg diffraction pattern. It happens to be of a zeolite, I think, as you might collect on a copper X-ray set in a lab. Now this contains our nice sharp Bragg peaks, but it doesn't actually give us much information on the local structure. And that's because we don't have much information at this really high Q range, which is needed to get the really local structure. When we're doing a total scattering experiment, what we typically do is collect out to very, very high Q, where all of our typically Bragg analyzed data set is down here at really low Q. And then we have this other part that looks basically like a flat line in an X-ray data set out to high Q. We then need to, this is our scattering experiment. So we have X-rays hitting our sample, typically in some kind of container. And the bit of all this the scattering of information is this coherent scattering. So that's what we're trying to drag out from this Bragg data set. In order to do that, we need to remove things like air scattering, multiple scattering, incoherent scattering, any fluorescence or Compton scattering from our sample. I need to take into account things about the experiment, such as detector efficiency or attenuation by the sample. When we can do that, we can obtain a data set which looks like it has a few more features in it. And we have this yellow line here is the amount of coherent scattering we'd expect if our material wasn't giving us any Bragg peaks at all. What we can do is divide through by that line, and we get this function here, which is then what we call our total scattering structure function. And this is exactly the same data. It's just been manipulated by such a way to give us this coherent scattering, and only that coherent scattering, and divided through by the form factor of our X-rays to give us something which is no longer dependent on Q. And it really emphasizes all this other information that was completely absent when we just looked at our Bragg data set. So like I said, this is exactly the same information as we originally had down here. But now, because we're dividing through by this form factor and correcting for these other features, we're seeing a lot more information. And all of this information here is due to short range effects in our material. Now, we could model this function directly, but what we find is it's actually a lot more instinctive to look at this, the Fourier transform of this function. And that's then what we call the PDF. So oscillations in our total scattering give rise to peaks in our PDF. And what we find is each of these peaks correspond to bonds or bond distances or correlation distances in our system. So this is it in numbers. I'm not going to dwell on this, but suffice to say that so long as we can measure our scattered intensity, correct it in the correct way, we can generate our total scattering function and Fourier transform it to get our PDF. But in terms of a more instinctive description of the PDF, it is just the probability of finding two atoms at a given separation. So this is our pair distribution function, PDF, and this is generated for this Alpo material here. And what we have are a series of peaks in our PDF, and they correspond to distances within this system. So this first distance here is this phosphorus oxygen distance. The next one here is a slightly longer aluminium oxygen distance. As we go to higher and higher R, we pick out different oxygen distances, and so on. Obviously, this gets more and more complicated as we go to higher R, because there are more and more peaks that might that exist in that R range. But it is entirely quantifiable. If we have a model, we can generate our PDF. And equally, if we have our PDF, we can try to generate a model which is consistent with that PDF. So it's used for the study of short and medium range order. And typically this used to be, the PDF used to be the domain just of liquids and gases. But increasingly it's also being used to look at crystalline and semi-crystalline materials. And that's because a lot of the materials people are now studying for applications are not as nice and crystalline as they might like to think. And what we're increasingly finding is that the disorder and defects that cause the change from a perfectly crystalline state is actually what's giving us rise to our interesting properties. So understanding that local structure is more and more important. And it's increasingly finding a wide range of disciplines, applications in a wide range of disciplines, such as materials chemistry, solid-state physics, sciences, pharmaceuticals, and so on. The list keeps growing. So in terms of the information that we get from a PDF, in terms of a very quick summary, the peak positions are giving us our bond lengths and our geometry of the atomic arrangement. Our peak widths are giving us information on vibrations and phonons and disorder within the system. So the wider the peak, either the more that the things are moving around or the more disordered there are, either there are wider distributions of bond lengths. The peak areas give us our coordination numbers or occupancies. And I should say for X-ray PDF, this is also correlates with the number of electrons for each of the atoms given in the pair giving rise to that bond. So if you have very high Z atoms, then the bonds from those atoms will be much larger than ones from lower Z atoms. And we can also give information on the size and shape of a system from how quickly the peaks damp as a function of R. So if you have a perfectly crystalline system, then in theory, these peaks will go on forever. Whereas if you have a nanoparticle, then the peaks will damp off very quickly and end up at a point where there are no more correlations. And that's because you've now reached the edge of your nanoparticle. So in terms of the information that you can just read straight from the PDF without any particular analysis, you can instantly get bond lengths. You can instantly get changes in coordination number very easily, although quantifying coordination number takes a little bit of modeling. And you can very easily get a maximum size beyond which you don't have any correlations in your system, just by seeing where you no longer have any peaks. So there are a lot of information present in your PDF, which you can get just by looking at the data set. So that's to comment on how the PDF compares with X-ray spectroscopies. And I'm by no means an expert in this. I tend to use XAS, Zane's XAS pretty much interchangeably. But they're also a probe used to look at the local structure of materials. And although the exact nature of the information changes depending on the Zane's or the XAS region, because they depend on the types of scattering events that you're looking at, these are still local structure probes to look at disorder and local structure in your system. But it is also, although it gives you the same type of local structure information, there are some critical differences between XAS and PDF analyses that we should go through. So the first is that XAS is element specific. And by that, I mean, when you're doing an XAS experiment, you're tuning to an element of choice. And all of the local structure you're looking at is a local structure around that element. It can also provide you oxidation state information of the element of choice by looking at the edge and its position and the shapes around it. And also, it's slightly limited in that you tend to only get information over the first few coordination shells. So here we have an example of looking at some different manganese species, and you can see the data's basically gone by 5 angstroms. So you're seeing the first couple of coordination shells, but nothing beyond that. So how does that compare to PDF? Well, in terms of the selectivity, XAS gives you that element specificity. So with an XAS experiment, you can tune to a specific element and look at the local structure around that. With our PDF, we're looking at all the atoms present in the material, weighted by their Z, i.e. how many electrons they have, and their concentration. What this means is that your PDF is dominated by the heaviest scatterers or the most dominant bond lengths. So if you're looking at a very, very small weight percent of one particular element, then XAS might be your preferred choice. However, that doesn't mean that PDF couldn't also provide you information about the molecular structure of all the other things that are present in your material. So the sensitivity, the PDF can go down to percent levels. So you can look at things around the 1% level, whereas XAS can go down to ppm levels for your element of interest. In terms of sample preparation, PDF is typically done on powders supported in capillaries or liquids supported in capillaries. If you have a self-supporting sample, you can just put that directly on and not have a container at all. But most of our experiments are done like this. Again, most XAS experiments are diluted and pelletized. So you have your powder sample and you prepare a pellet from it, typically diluting it down. But that's not always the case either. In terms of the types of sizes of sample that you can get with the two techniques, in terms of how penetrating the X-rays are when we're doing these experiments, for PDF, we can get away with relatively thick samples of the order of a few millimeters. Whereas in XAS, depending on the mode you're collecting in, but typically for transmission mode, you're looking at relatively thin or very dilute samples. In terms of the range of the data, PDF can give you data in excess of 100 angstroms if you so wish. Typically, though, people only model up to around 50 angstroms. But crucially, it's giving you information all the way from the shortest range up to long-range data to fully plug the gap from that is completely missing from your BAG data. So it goes all the way from the shortest range up to your long-range structure. Whereas with the XAS, I mean, you can argue about the numbers a little bit, but yeah, it's only the first few coordination shells where you can get really good information. So around the 5 to 12-ish angstrom range. So on the oxidation front or the electronic state of your systems, PDF does not give you any information about that unless you can infer it from the structure, which the PDF can give you. That's a relatively rare case, whereas the XAS can give you the information of the oxidation state. In terms of the timescales of the experiments, they're quite similar. I've put on the order of seconds to tens of minutes for both of them. Again, you can go shorter depending on the type of PDF and type of XAS experiment. And you can need to go longer if you go for the really precise ones for both of these cases. But they have quite a nice similar requirements for data collection times. But really what I want to emphasize here is not about necessarily which one of these is always better, but the complementarity of the two techniques is really what I'm trying to push. They're both local structure probes, but both of them give us different information. Our XAS is great at giving us information around one specific element, but it's relatively limited in terms of the range of data. And you can end up in a situation where if you have exactly the wrong pairs in the wrong positions, you don't necessarily see much of the local structure at all. Whereas your PDF data set will always give you some information. And really the ability to use both of these data sets together is where the real power is to get true local structure information. So that's a brief introduction to how PDF relates to XAS. And I'm going to move on to how we get the best quality PDF data. And what it comes down to is actually very much the same as with XAS. With XAS, they call it K, we call it Q, but we want to collect our data out to as high a Q as possible, where Q is this 4 pi sine theta over lambda. What this means is we want to collect out to as high an angle as possible and as low a wavelength as possible to get our maximum Q. If we were to try to collect a PDF data set of this setup, of this aluminium this Alpo system, as we saw before, if we were to do that on a standard Bragg diffractometer with copper radiation, this is the type of thing that we'd see. And it's kind of a broad mess with not much detailed information in. You can do PDF in the lab, though. You can get a molybdenum source, which starts to get you slightly better information, or a silver source, which is about as good as you can get in the lab. And here you can start to see more resolved features. It's particularly this first bond. Now you can see it starting to look like a peak with a significantly pronounced shoulder on it. But as we go to higher and higher energies, then you start to see these peaks fully resolve, and you get to a point where you're getting much more detailed information about your system. Ultimately, if you, so the amount of information is ultimately limited by the sample, or how much the sample is moving. So you can't just keep going to higher and higher Q and expect to keep getting sharper and sharper data, because your peaks are ultimately limited by how, the thermal parameter of how much your atoms are moving. But typically, you'd want to be collecting out to in excess of 25 inverse angstroms for a lot of systems. So that's the high Qmax requirement to give us this good resolution in real space, so you can see detailed information about our local structure. We also want to collect with high flux, and that's because our X-ray fall factors, so how strongly our X-rays scatter, fall off very quickly with Q. So here's just a random selection from the periodic table, some gold, iron, and copper, so gold, iron, and carbon. Their form factors as a function of Q, and you can see they drop off very quickly. So if we're trying to collect really good information at high Q, we struggle because we get very little information scattered at these high angles. So what that means is, in order to get good information, we need a really high flux. We need a low and reproducible background. What that means, if we're interested in our sample, in this case some Pringles, we need to have a container, which ideally gives us a minimum amount of scattering, but also that we can measure the container itself without any Pringles in it, so we can subtract the container from our Pringle measurement. And then we can just get the PDF of the thing of interest. That does have some implications for in situ experiments. And typically what that means is that we can't always just use an in situ setup that you might have had from a different beamline. But what we are very keen to do is develop in situ experiments that work well for PDF. And what we tend to find is that if it works well for PDF, then it works well for other systems. So it's just a warning, really. If you have ideas for in situ experiments, give us as much notice as possible so we can do the work and testing to make sure that we'll get not only data, but good quality data by having this reproducible and ideally low background. And the other thing that we need is a moderate Q resolution. And by that, I mean the Bragg data sets that we get don't have to be the best in the world. So here is a nice sharp Bragg data set, as we might get from a beamline like I11. And that gives us the PDF on the right, where we'll see features out, and they would go to as long as you care to look, really. Go to very, very high R. So if you wanted to model your PDF out to hundreds and hundreds of angstroms, then you'd need very high resolution. But with very high resolution, often means that you don't collect as many photons, and what we really need is flux. So what we typically do is reduce our resolution by pushing our detector really close to our sample. It gives us broader peaks, but actually that doesn't degrade the low R information at all. What it does is damp the signal as a function of R. So when we look at the really low R region, despite the fact that we've got quite broad peaks now, it's done very little to impact on the low R structure. And since most of the time we're looking at that really short range information, that's what we do. We compromise our Q resolution to get really high flux and preserve this information at low R. So that's what we need to do to get good quality PDF data. Fortunately, you don't have to worry about that, because what we've done is build the XPDF beamline. So this is on the I15 position on at Diamond. I15 is the extreme conditions beamline, which is around at Diamond for, well, since it was one of the first beamlines built at Diamond. And more recently, we built a side station to that called I15-1, where we do our XPDF data collections. It's a station dedicated to PDF collections. It's allowed us to do it. We can do PDF at 3 different energies, 40, 65, and 76 keV. We typically spend all of our time at the highest energy because it gives us the highest resolution. It's a very high flux beamline. This allows us to collect PDFs in seconds if we need to, although typically our data collection times are around the minutes to up to 10 minutes. And we can do things to increase the flux more by changing our bandwidth. But that's typically only done for the really fast experiments. The other things we've done when we designed our beamline is give it a really low background so that the beam travels down in this direction towards our detectors, and the beam's completely contained in these tubes to make sure it's really nice and clean by the time it leaves and hits our sample. And it's also a highly stable beam. And what I mean by that is that the intensity is very consistent, and it's also monitored with our I0 monitor. The sample end looks like this at the moment. We have 2 detectors. We have our PDF detector, the one that's close to the sample. So that's pushed close to the sample so we can collect as higher angle as possible. And when we're collecting our data and integrating it, we're collecting around this arc here. We've also got this, so I said that gives us a not very good Q resolution. So we have a second detector further away, just because it gives us higher resolution BAG data. So sometimes if you're looking for a phase change, which is very obvious in your BAG data, but not so obvious as a function of Q, then we can use both of these detectors together to give us very good information for the PDF, but also pretty good BAG information. I say this is what it looks like now because later on in 2022, we're installing a completely new detector system and end station. This is called the XPDF ARC detector. And this should revolutionize the speed at which we can do data collections. I don't have numbers for that yet, but I expect we'll be able to go to sub-second PDF data collections for in-situ work pretty easily. But more information on that as we commission it later in the year. So our standard experiments, we can offer a high and low temperature very easily from 100K to 1000K. That's done using this cold gas system and a hot gas system. We developed some of our own sample environments. So this is a hydrothermal cell, which can do experiments in sealed quartz capillaries up to 200 Celsius, 473 Kelvin. And this way we can look at things like in situ formation of zeolites in completely sealed hydrothermal setups. Do quite a lot of battery work on the beamline. This was an in situ setup we developed to look at the in situ cycling of battery materials. And we've done a fair amount of liquid work on the beamline. This is a liquid flow cell. Actually, this is also used for looking at ion exchange. So this was an ion exchange experiment where we had some kind of, I think it was a zeolite in here as well, actually, where we're flowing different solutions through and ion exchanging the materials. And the thing that all of these have in common is that they have very low and reproducible backgrounds for our experiments. So that's the kind of thing that we can do with the beamline. I'll go into some more details later on. But now I want to talk about what we do with the data when we have it. So PDF analysis falls into a number of different categories, and the complexity of that analysis kind of changes quite a lot depending on how much information you want out of your system. So in terms of the very easy things you can see by looking at the PDF data, you can get a lot of qualitative information and semi-quantitative information actually about things like the bond lengths in our systems. As I said, it's very intuitive. You can see a peak, you know that you have a correlation at that distance. And if you know what elements are present in your material, you can often very quickly say, oh, well, that is that peak. So you can see the bond length. And if you're doing an experiment, you can see how that's changing as a function of time, temperature, or whatever it is you may be changing during your experiment. And that gives us a very easy way into model checking. And by that, I mean, if you have a model of a system, be it from a SIF file or from a DFT calculation, you can calculate the PDF very easily and compare your bond lengths, compare the PDF in total. And it's a fully quantitative data set. So if your model doesn't agree with your observed PDF, then you know your model is wrong. It's really powerful for checking models from different types of simulations against your real observed local structure. Because if the PDF matches, then you've got a good tick to say, yeah, my model's consistent with that. It's probably right. If your model doesn't match your PDF data, you know it's wrong. It also gives you qualitative information about coordination numbers. So in your in situ experiment as well, you can see where bonds are forming or where bonds are breaking, because you can just look at how big your peak is as a function of time temperature. We can also do statistical methods. This is similar to people that do XAS, where you look at, or XAS, sorry, where you're looking at how much of each type of oxidation state is present in your systems. You can do that kind, or looking at principal component analysis of your data sets. You can apply those kind of statistical methods to PDF data sets as well to see where your data is changing and by how much. So those are the relatively easy types of analyses to perform. And then it gets a little bit more tricky in terms of the quantitative analysis or fully quantitative analysis. You can do small box modeling. And by that, I mean, you have a structural model where it's a small box, it could be a unit cell, or it could be a slightly expanded unit cell, and you do a refinement on that in the same way as you would have with your BAG data. And that gives you information on the kind of crystalline elements of your structure. Or if you're going to a unit cell which is larger than the crystalline one, it gives you information about where your crystalline structure fails on the local structure and what things need to change to match your local structure. And then on the other end of the complexity scale are these big box refinements. And these are where you're trying to model your disordered system by throwing a lot of atoms at it. These are typically done via an RMC refinement. And then you can generate you generate a large box of atoms that are completely consistent with your data sets. And then your job is to try extracting meaningful information from those data sets, such as, well, what is my typical local structure? What are my coordination numbers of these different atoms in this box? And you can also use molecular dynamics type methods to also feed into these large box refinements. So what they look like, so small box modeling, you're using a unit cell type refinement. Often you do some element of symmetry lowering, so you're not using your crystalline SIF file. You're doing something to lower the symmetry of it so that you allow your local structure to change from that of the crystalline system. We go into some kind of supercell, or you're doing what's called a Boxcar refinement, where you do refinements over small ranges of your data at lots of different points along the data. So there you're seeing, well, what does my unit cell look like if I only look at the first 10 angstroms? What about the next 10? What about the next 10? And that shows you that trends that are present only on the very short scales and trends that are present only on the very long scales. On the large box modeling case, you end up with a system that's this, where you have a large box of atoms with lots of different coordination numbers within it. These refinements take quite a lot of care because you want to make sure that you allow it to have, you give it as many chemically sensible constraints as possible to make sure that you are moving your atoms around in as sensible a way as possible. And then also it can take some time to extract the meaning information from it. So if, for example, you wanted to look at just tilts of certain octahedra within your material, then typically after your refinement, you then have to do the analysis to extract that information again. But fortunately, there's quite a few tools around and freely available to help you with those types of analysis. Other types of large box modeling include population analysis when you're looking at nanoparticles, and we've got an example of that later on. Okay, so I'm just going to move on now to some examples of PDF analysis as applied to catalysis systems. So, framework materials, I believe, are fairly commonly used in the types of work that you do. And by frameworks, I mean things like MOFs and zeolites. And here's an example where a big box method was used to study metal organic frameworks when they became liquids and glasses. So this was a MOF framework, which was heated up to the point that it became molten, and then they could quench it down and form a glass again. And by using this type of big box, they were able to model what the liquid and glassy states look like. And through that, they were able to extract chemical configuration information, such as the coordinative bonding, and also look at the porosity of the system, because they were looking at these things for uptake and purification of gases. And they were able to correlate the porosity of the model with the porosity as observed by physical methods. So that's some of the kind of very complicated but information that you can get from really quite complicated systems, but with this kind of big box modeling. Then there's a lot more information you can get out. This was a study done what I'll call model checking, i.e. by collecting the data and then verifying the PDF data against different types of models to assign different peaks and therefore gain an understanding of your system. This was from UIO 66. So this was the crystalline sample that they had, and then they amorphized it. I think this was through ball milling. Oh yeah, from ball milling. So there was absolutely no long-range structure information on this material at all. But they wanted to know, well, what is the local structure? Are, for example, these coordination environments preserved around the zirconium? And what they were able to do was look at the PDF of the amorphous system. By looking at the model of their cluster, they could easily assign different peaks to the different features in the PDF. And they were able to see how the clusters themselves were maintained on amorphization, but how the distances between the clusters broke down very quickly. So here we can see the models where in light blue is the amorphous sample, in dark blue is the crystalline sample. Pretty much all of the features due to that cluster are preserved. And then as we go out to this higher R where we're hitting the distances between clusters, and there are some peaks, but they're much broader and they're much more subdued. This instantly shows you that although the clusters are maintained, correlations between the clusters are significantly weaker. I should say as well, a lot of these systems aren't done in isolation. Same way as I was saying that PDF plus XAS is a very strong combination. Here they also used NMR to verify the same kind of results around what's happening as they amorphize the sample and what's happening to the zirconium in this case. Sorry, this is the carbon-13. Other things you can do via model checking. This was a MOF that they managed to cut up either through grinding or sonication to break these weaker layers between some sheets and produce basically 2D nanomaterials of these single sheets of MOFs. But again, what is the structure at this point? They wanted to know, they knew that they'd lost a lot of the long-range structure because their BAG data had almost completely disappeared when they looked at the BAG data set. But they wanted to know how much of the crystallinity is preserved. And here again, just through simple model building and comparison, they could see which features from the layer system that they were looking at were preserved, as they did different types of sonication and different types of mechanical separation. And they found that grinding basically gave them very, very small units with very little extended structure, whereas depending on the method of sonication and the original form of the UIO 66, they could generate different length scales of these sheets and different coherence lengths of them. There's also some statistical methods you can apply. This is an example in the MOF literature where they applied a statistical method known as non-negative matrix factorization. This is a smarter version of principal component analysis, basically, where we try to where we can look at differences between data sets and extract populations within that data set. So this is where they're looking at they're looking for a zero thermal expansion material in a MOF. They were tuning between a completely zinc and a completely cadmium MOF, and they used NMF to explore the parts of the system that looked like the pure zinc MOF, the parts of the system that looked like pure cadmium MOF, and then isolate the bit of the data that's from this zinc cadmium part. So by just doing that technique, by collecting lots of PDFs and applying NMF to it, they're able to extract what the new bit of the data looked like and show what this zinc cadmium MOF part of the system, show the PDF of it and extract information about its structure. There's also plenty of in situ studies that can be done on this type of system. So here's an example from a flow reactor where people were looking at the formation of these things. Because PDF isn't limited to looking at crystalline materials or liquid samples, we can look at everything along the way. It's very good to look at in situ formation because you get information from the starting materials, the intermediate clusters that are forming as the thing's growing, all the way through to the crystalline products. And in this type of analysis, then you can do, full-on model building to fully describe all the features in your PDF. And that then could be quite a significant amount of work to fully show how these clusters start and then grow and ultimately go on to form the crystalline system. And if you want to know that really detailed information about the mechanism of formation of these things, then that's what you want to do. But if you're just interested in the length scales of how ordered things are at what point in the startup, but at what point in the synthesis, then that information is just instantly available by looking at the PDF. So here at room temperature, we see that we have no correlations beyond, really around 6 angstroms. And as the reaction goes on, we see significantly stronger correlations at higher and higher R, up to the point that we see after 32 minutes, this more crystalline region here. So, like I said before, the amount of data that you want to get out of it is a very important part of a PDF experiment because it depends on the complexity of not so much the experiment, but of the analysis and the amount of time it's going to take to get useful information out. But there's very, very useful information that you can get with very minimal effort, because as I said, you can literally see when peaks finish in order to see how coherent your system is. Or you can go to the extent of modeling fully the system, and then you can get information about clusters as they're growing and their structure as well on the way. I should say a note on this point is that the speed of experiment depends on the concentration. And by that, I mean, if you're looking at, if your MOF will only form when the metals are present at 1% level, then we're going to have to be collecting each of those data sets for maybe 10 minutes to get enough information to fully extract the information that you're interested in. Whereas if your MOF's present at 25% of the total concentration, then we can be running the experiment much quicker. So that's something to note when thinking about and planning these experiments. I should say as well, there's a really nice review that's recently been published from Patero Pratt's group. And I'll just leave the reference here. I'll make the slides available through Martin Warning. So if you're more interested in this type of system, then there's a really nice summary of the types of studies that are in the literature here. Another thing that I believe is done quite a lot in the group are work on nanoparticles. So nanoparticles are a very good thing to look at with PDF because, again, they're things that have a limited length scale of structure. So often the Bragg data is not very good. whereas the PDF data gives you all the information about how the particle extends as a function of R beyond just the shortest bonds, all the way up to where then you start seeing it in the BAG data. We have very large crystallites. So it's very good for looking at nanoparticles and their formation. Here's an example where you can also not only look at nanoparticles themselves, but what's happening on their surface. So here we had some 15 nanometer iron oxide nanoparticles. And through some very delicate extraction of differences between data sets, we're able to extract this double difference PDF where we're just seeing interactions of solvents on the surface. And here we were able to extract meaningful features corresponding to hydration shells on top of the nanoparticle surface. There's a few caveats for this. You need to have well-behaved nanoparticles, so they can't be changing as a function of anything else happening around the system. But if you do have that, and you do the experiment very carefully, then you can extract this kind of meaningful information, which is not very accessible by other methods. These differential techniques are really helpful in PDF, not only because they give you access to, that's the way we generate the better sensitivities with PDF down to the kind of percent levels, by having something to subtract from your data. So if you have your material of interest in a solution, then we can measure the solution separately and subtract that signal. If you have a particle of interest on a support, then we can measure the support separately and subtract that signal and get back to the information that you're interested in. Here's an example of exactly that, where there was a study looking at the reduction of nickel oxide on this series support. And they're able to subtract out the support because it was not doing much from a structural point of view during the reduction. And they're able to see species of this nickel oxide go into nickel metal. And these were species that weren't readily identifiable from BAG data because they're nanoparticulate. But in the PDF, they're easily able to pick out these different features from nanoparticulate nickel metal and nickel oxide. You don't just need to model nanoparticles as if they're bulk. You can get quite a lot of information about nanoparticles by doing, again, slightly more complicated analysis. Fortunately, there's packages for it. This one's called the BUSI. Just very quickly, this is how it's kind of laid out. There is a GUI for doing this. But when you do this type of analysis, then you can get size and shape distribution of the nanoparticles. And here's a study where they're looking at iron oxide, where they're looking at the different forms of iron oxide within nanoparticles. And when you do this correctly, then you can not only extract sizes, but you can also extract shell sizes for different, this was different oxides within one nanoparticle. So this is a core shell particle that they're able to fully model using the PDF and total scattering data to extract the core and shell, the core size and the shell size of these systems. So as summing up, just some golden rules for when you're, hopefully this talk's given you some ideas for the kinds of thing you can do with PDF. But in terms of moving that forward into proposals for your BAG, some rules to consider are, number one, discuss your ideas as much as possible beforehand. The BAG panel and XPDF staff are going to be more than happy to talk to you about your ideas. And the earlier that you can do that, the better, because then we can go from, ooh, is this a possibility, through to a well-rounded experiment when in advance of actually doing the experiment. When you're doing that, though, do really clearly think about what it is you want to do. I know that's kind of a simplistic thing, but with PDF, it's really not just about the what, it's about the concentrations, the timescales that you need, and so on. And they all come into the factor of, is this a good PDF experiment? Because if you want to do it, but then it's only at ppm levels, then we can't do it. Maybe that's an XAS experiment. Do really think about why you want to do it. Why is PDF going to help? And things like in situ experiments can be done a lot more easily in a PDF experiment than some others, because the high energy that we work at means that we can go through a lot of different materials. And it means that we can, sorry, I'm just going to skip that experiment. So when you're putting down your ideas and proposals, do remember, still make sure that the BAG panel who are going to review this know why it's important scientifically and why it's exciting to you. But do also remember that the BAG panel are already an expert audience, so you don't need to necessarily go back over to them like why catalysis is important and explain what PDF is. They already know all that. So focus on why it's a really important experiment for the BAG. And when doing a PDF experiment, it's really important to do the hows you're going to do it, how you're going to do the experiment, but also how are you going to analyze your data. Because what we really want to do through this BAG is to not only collect really good data, but it's also to have some really good analyses coming through the BAG group. And that takes a bit of thought beforehand. Because if you just collect data without an idea for how we're going to analyze it, then that could end up being a very open-ended thing. So, like I said, it comes out to rule number one: discuss it with us beforehand. We can come up with a plan for not only how we do the data collection, but also how we're going to analyze the data. And that kind of thought beforehand means that we can hopefully be looking at for the signs that the experiments are working as the experiment's progressing. And that's really valuable to make sure that we make the most of the beam time. So I'm going to be more than happy to take your questions, and I think I'll leave it there. The contact for the BAG internally is Martin Wilding. You can email xpdf@diamond.ac.uk to contact with the beamline staff. And that's it. Thank you very much for your time.
Thank you, Phil. That was a really interesting talk. We've had lots of questions coming in while you've been talking, so I will go through them and read them out for you. So first is from Matt Potter, who says, thanks for a really good talk. Is it normal practice to freeze samples down, say, to liquid nitrogen temperatures to limit thermal motions and get better resolved data at higher energies?
It depends what you're interested in. So it is really good to do that, so long as your material is not going to change, and if you want to have the really high precise system. But a lot of people are interested in what their system's like at room temperature. So it's important to have a caveat. Yes, collect the low temperature information, because you do get the highest resolution by doing that. Everything sharpens up as you go to colder temperatures. So if you're trying to get a really precise structure, then that's really good. Just be wary that your system is still the same when it's cold as it is when it's at room temperature. So generally collecting both is a good idea.
Thank you. You may have answered this a bit later in the talk, but Satyam asks, what sort of in situ experiments can you perform with PDF at present?
Yeah, so there's the hydrothermal cell to do in situ heating of sealed systems. There's the liquid flow cell where we can do kind of different volumes for different timescales. So we have a syringe pump setup where we can do quite fast flows, and we've got a perio pump setup where we can do quite slow flows. We're working on our own heated setup for that, so you can go up to moderate temperatures. We do also have our own gas cell, but that's been through a number of iterations and kind of needs another reworking before we do that fully. But that's on very much on our list of things to do, and I have a feeling that will be high priority for this group. So we'll be prioritizing that as we get the requests in.
Brilliant. And if people have cells that they've used on other beamlines, is it worth talking to you about them, see if they would fit? Or
absolutely, it's rarely the case that it won't fit. It's just down to how good a data it is, and that pretty much comes down to the exit angle, because we need to collect out to a really high angle. We want a kind of an uninterrupted path from all the way through your sample all the way through the detector at in excess of 45 degrees ideally. So it kind of depends on that geometry. But often we find that it's either possible already, or with a bit of modification, then we can do it. But yeah, well, more than happy to have those conversations and share drawings and so on.
Brilliant. So Matt says that you mentioned that there are 3 possible energies on I14 1. Are there any benefits or additional structure information that can be gained by different energy values or comparing different energy values? What does it give you?
Yeah, so yeah, good question. So 40 kV is typically used for organic materials, where we can benefit from having slightly higher Q resolution because you get slight information that's a slightly higher R. but also they're just at our highest energy, most of the X-rays go straight through. So reducing energy, you get a bit more interaction, and we can collect at higher flux as well at lower energies. So it's more about the signal quality than anything else. Also, the kind of organics tend to be a bit floppy. There isn't much information beyond a Q of 20 odd. So going to 40 kV, you don't really lose out much, you only gain. Whereas the in situ experiments, where again, you want to be as forward facing as possible, we go to the highest energies. And most, we pretty much only use the intermediate temperature if we have like iridium, which has an absorption edge near 76 kV. And we want to avoid that because we just have massive fluorescence and a massive background. So the 65 kV is pretty much only for that. The other benefit is if you have something that has a lot of very low angle scattering. So if you're looking at very small nanoparticles or things where you know you've got small angle scattering, then going to a lower energy can just make that a bit more visible on our data, because we have a beam stop, which will cut down everything at the really low Q. If you want that signal though, then yeah, that can be a problem at the highest energies. So yeah, it depends a little bit on exactly what system you're looking at. But even things like zeolites, we can still do that at the highest energies. It's only the really large unit cell things or things with a lot of small angle scattering that we change the energy for that.
Okay. So Donnie asks, how much does temperature influence PDF, and what is the maximum thickness for the sample? And are there problems for self-absorption?
Okay. So, well, the self-absorption part is, I'll start there. It just depends on how absorbing your sample is at 76 kV, and that's the same for the thickness, really. So in theory, we can measure and have measured samples that are 3 to 5 millimeters thick. You do start to notice that thickness in the quality of the data. Not so much in the PDF, but in the BAG data, it really starts to broaden it quite a lot because your sample's broader. So you're getting diffraction from a larger range of data, a larger range of space, so that broadens your peaks. So we try not to go really, really big. Typically 1 or 2 mil is kind of the sweet spot. I've kind of already forgotten the first part of the experiment now, first part of the question now.
I mean, I assume that's other than the motion of the molecules affecting the sharpness of the peaks.
Yeah. So yeah, as you go to higher temperatures, then yeah, it's moving around more. The peaks broaden, but there's no conceptual limit to what you'd see, other than yeah, at some point things melt and you get less information, but it's still a reliable quantitative picture of what's happening in your system. It's just your system's very disordered.
Donnie also asks, how much is the high flux affecting the material, for example, beam damage?
Yeah, so we don't tend to notice it that much unless we have pretty much MOFs with a metal near 76, with an absorption edge near 76 kV. So we've measured some like hafnium moths, I think, where we had significant absorption from the metal and a weak floppy organic bit, which gets destroyed by the absorption. So that is your worst case scenario. But apart from that, we don't tend to notice beam damage in any way near things like the I11 beamlines or the X-ray absorption beamlines, where intentionally they're having things absorbed into your material. Most of the X-rays go straight through, which is annoying for collecting the scattering information, but it's pretty good in terms of minimizing beam damage.
Sudesh asks, is it possible to differentiate nearest neighbours in the periodic table, e.g. nitrogen and carbon, when they are in similar interatomic distances?
No. Short answer. Yeah. So yeah, if the peaks are completely overlapping, and you can look at how the minimum difference you can get depends on the maximum Q that you go into. But for carbon and nitrogen, the bonds are always going to be overlapping, really, because they're so close in distance. No, you will not resolve it. What you can do is obviously model the system, and if it's consistent with the model, then you can be fairly sure that the model is correct. but almost certainly if you swap the carbon and nitrogen around and remodeled it, it would have exactly the same fit. So I'd say, yeah, no is the short answer.
So, and Jay is asking if you could elaborate a little bit on the technicality or limitations in measuring bimetallic core shell structured nanoparticles in PDF.
Yeah, okay. So it very much depends on how different the structures are. And if you have multiple metals, then how different in Z they are, or how different their sizes are. So it all comes down to, how different their PDFs are with you. And you can tease out a surprisingly large amount of information using that kind of Debussy method of analyzing the data. And I can point you out some other publications using it where they've got information out which is not, it wouldn't necessarily expect to be able to go into the sensitivity that they can. But I think they've intentionally chosen bimetallic systems where they're quite different scatterers and so on. So it very much depends on the system, and I'm more than happy to have the conversation. Like I said before, what's really good with the PDF is you can easily model it and easily calculate the data. So if you've got a question, am I going to be sensitive enough to this? All you have to do is come up with a model, calculate its PDF, change the model, calculate its PDF again, and then you'll see instantly, actually I am or am I not sensitive to that particular change. So it is very, very system dependent, which is bad, but it's very easy to check before the experiment, which is good. Okay.
Well, as we can see from the questions, it's been a really sort of amazing webinar. It's been really sort of, I think everyone's really enthused by it. So thank you for coming to talk to us, Phil. And we look forward to submitting applications.
Look forward to it too. And feel free to drop a message anytime. Have to meet in person if people want to talk through things. And hopefully we can generate some great ideas and some great science.
So thank you all for coming. Please do check out the Catalysis Hub webinar pages for future webinars. If anybody would like to get in contact about the bag, please contact Martin Wilding. You can find his contact details on the bag pages of the Catalysis Hub website. We look forward to all the outcomes of the PDF bag and watch this space. So thanks again, Phil, for joining us.
Thank you, Josie.